Welcome everybody to the NGI Technical Podcast. The NGI Technical Podcast is a podcast from experts for experts, where we have in-depth talks about technical topics in the domain of NGI's work. My name is Georg Erharter, and I'm an engineering geologist at NGI with a PhD in civil engineering from the Graz University of Technology. I was living and working in Austria before, and I've been moving to Norway to explore more fields of geotechnical engineering. Today, I have the great honor to talk with Professor Herbert Einstein. Professor Einstein is a legend in the field of tunneling, and we have this podcast after having both attended the first International Rock Mass Classification Conference in Oslo that happened in October 2024. Herbert agreed to being a guest on the podcast now after the conference, so during our talk, we will every now and then refer back to what happened at the conference. But in general, we will be talking about tunnel design methods, tunnel construction, so it is an independent podcast and not directly connected to the conference. Professor Herbert Einstein did his dissertation at the ETH Zurich in 1966. The title is in German. I will read it out in German. It is Die Schärfestigkeit dreier kohäsiver Böden in Abhängigkeit vom Lagerungszustand und von der Materialart. After doing his dissertation at the ETH, he moved on to the US. And he's leading the Herbert Einstein Research Group at the Massachusetts Institute of Technology, so MIT, since 1973. Herbert's main fields of work, or main topics of work, are rock mechanics, engineering geology, underground construction, field measurements, laboratory experiments, numerical and analytical modeling, and many more, as you will see in this episode today. So it's quite amazing that he, as a very experienced tunneling professor at the age of 87, is dealing with state-of-the-art topics like artificial intelligence as well. Herbert has been teaching in many university courses at MIT and abroad. He in total has published, or he has contributed to 151 theses, including 33 PhDs throughout his career. He has received several teaching awards for educational and mentoring excellence, and conveying information to the next generation is very important for him. He has authored or co-authored over 300 papers, and he also received several very prestigious awards. In 2006, he received the award from the American Rock Mechanics Association for outstanding contributions to rock mechanics, and in 1999, he even received the famous Miller Lecture Award from the International Society for Rock Mechanics. Enjoy this episode about tunnel design methods and tunnel construction, where we are talking about tunneling from the very beginning, going back thousands of years, and we take a look into the future. Welcome, Herbert. It's very nice to have you on the NGI Technical Podcast.
Okay, that's great. And I want to congratulate you for this absolutely fantastic Congress, the conference. That was super. I learned a lot, so I'd like to thank you for that.
Yeah, thank you. That's really great to hear. That's a very big honor, yeah. We want to talk today about tunnel design and about tunnel construction.
Okay.
And I think to get into the topic, I want to start with a basic question. What would you say is the main difference between designing and constructing a tunnel versus designing and constructing something above ground?
Well, the uncertainty of the geologic environment is the main thing that's different. And that causes possibly cost overruns, and certainly if you look at the highway above ground or a railroad above ground versus a railroad and tunnel, it's always more expensive. I wouldn't say always, but in most cases.
Yeah. So. What are these uncertainties that we face underground and that we don't have above ground?
You basically, above ground, the ground is what supports the structure. In the tunnel, it supports the structure, but also it loads the structure. So then it has two aspects in contrast to above the ground. So then the uncertainty which you have above ground too is twice, because you have it as a load uncertainty and you have it as a support uncertainty. So that makes it more difficult.
Yeah.
And then also the access, usually if you do something above ground, you have an easier access to explore in contrast to below ground. So these are the main differences.
Yeah. I would also think that especially the geological materials that we're dealing with underground also has quite an impact, right? Because it's a much more, let's say, unpredictable material than everything we deal with above ground.
Yeah, but you still have a foundation. You still have the ground characteristic uncertainties. But as I said, the main difference is that the ground difference uncertainties are not only on the support side, but also on the load side. So that's a double uncertainty that you have to deal with. And then the greater difficulty of accessing the ground, because you basically have a whole horizontal or vertical or whatever, and you need to know ahead what's going on, and that's very difficult.
Yeah.
And so the foundation where you can go from top down is much easier.
That makes sense, yes. What are then, because I mean, essentially people have been constructing and building tunnels for thousands of years. The Romans already have done it. Over time, how were people able to deal with this uncertainty? What were the tunnel design and construction methods that evolved over time?
Well, that's a good question. Basically, we have to look at two things. There were civil tunnels and mining tunnels. And basically, people simply dug into the ground, and then they ran into whatever they ran into. Anything with the Greeks to the Romans, then in the German and Chinese, quite clearly area, a lot of mining. So they basically dug into what they wanted to get out. In the case of mining, they wanted to get the material out to use it. And in the case of civil, they basically wanted to get the whole. But the attitude, simply go ahead and see what happens, that was the only thing they could do.
Yeah. Do you know how did people navigate underground, especially in these ancient times? I imagine in today we have modern geodetic measuring systems, but back then this was not possible. How do you find your way around the underground in ancient Rome?
Well, they had a plan. You know, the water supply of Rome was very sophisticated, and they actually. One of the cases was the Alban Lake, which they approached from underground, and there was a very sophisticated way of getting into an existing lake without killing the people in the tunnel, which the Norwegians have a lot of experience with. They have a very sophisticated way of getting into existing lakes. But the Romans, in that particular case, and then the other one also, they also managed to basically use an existing lake as a water supply reservoir and accessed it from underground.
Okay.
So that was pretty sophisticated what they tried to do and then also managed to do.
If we move then over time, how is it today? What are the main design methods for tunnels?
If you look at the way we construct the tunnel, we have these sort of so-called characteristic curves. And the characteristic curve is the ground is unloaded and the support is loaded. And so you have the support load going up and the ground load going down. And at the point they reach an equilibrium, that's basically the underlying principle for whatever, if you do it analytically, numerically, and so on. This is basically what you do, that you reach that point of equilibrium where the load on the support equals the load in the ground. And that's one of the main principles, is that you actually unload the ground and mobilize the resistance of the ground as you unload it. So if you were to simply put a support in the existing ground, the stresses on the support would be much, much higher than it is, because you do this, you have this unloading process of the ground as you build the tunnel. So that's the basic fundamental principle of tunnel design. Then whatever you do, be that an analytical method or a numerical method, or what we talked a lot about in the conference, empirical method, that's always the underlying principle, independent of what you then do afterwards to design the support.
From these three main paradigms, analytical, empirical, and numerical, what came first, and why do you think that is?
Well, as I mentioned in my presentation in the conference, this is kind of interesting because the tunnel design as a sort of a engineering method came only about in the second half of the 19th century, when they built all these railroad tunnels. But at that time, interestingly, there were some analytical methods developed already. I mentioned the one by Ritter, but there were others also. And then Rankine, quite clearly, obviously. And then actually before that, if you look at retaining walls, Coulomb even earlier than that. So there were analytical methods in the Renaissance area, and then particularly in the second half of the 19th century. But then, as I also mentioned, that Ritter said, in addition to having his analytical methods, you also look empirically at what goes on. So basically, when you build the tunnel, you have your analytical solution as a way to go, but then you need to look what happens, which is, again, we get into these uncertainties, or the variability, may be a better expression, to then consider this, the actual conditions in the ground, which are more complicated than what you assume usually in the analysis. And then quite clearly the numerical methods starting sort of in the 1950s, 60s, that's a completely different development.
But so when there have been analytical methods already in you said in the Renaissance period, right?
Well, Coulomb,
yeah, okay.
That's post-Renaissance, it's early 18th century.
Yeah. How does this fit with empirical methods, which are
that Coulomb did, as far as I know, Coulomb did experiments, but not in an empirical sense. He used experiments to validate his theory. But so that I wouldn't call this empirical, because he basically was a very well planned experiment to validate his theory.
But coming back to the uncertainty now, when we just stick with analytical and empirical methods, where do you think, or which method has the greater capability to deal with ground-related uncertainty?
I think it's the same. One is more formal. In the empirical methods, by definition, you look at existing cases, and based on existing cases, you compare to what your new case is, and the existing cases basically reflect the uncertainty because they're all different. And then you need to make a decision where your new case is relative to the existing cases. So that's what all these, we call them rock classification methods now, or call them empirical methods. That's the principle. So you have lots of them, and you try to get your new case as close as possible to one of the existing ones. And the spread of what's happening with the old cases, that reflects the I wouldn't call uncertainty, I would call this the variability, because you have different cases. But then in each case, quite clearly, you have a local uncertainty in addition to the fact that one case is different from the other. So you have, in a way, a double variability / uncertainty.
And Now speaking about numerical modeling, so when this came up in the second half of the 20th century, how is this different to analytical and empirical tunnel design?
You can do more because you can build these numerical models in an incredible amount of parameters including, which today quite clearly you could do this with computers. If you have a very complex analytical methods, the computing capabilities are also advantageous for that. But numerical methods you can play around even more because you can simultaneously vary geometry, material properties, and so on and so on. So that quite clearly for final design, I think, I don't know exactly worldwide, but certainly anybody who does a final design will do this with a numerical method today. The analytical methods, which are simpler, are usually used in a sort of a first step. And some of them are relatively straightforward to use, where you don't even need a computer, you can use a calculator.
Given that you're now around 60 years in the business in tunneling?
Sort of, yeah.
Sort of, yes. Do you see trends over time, how people do design?
Well, what we just discussed, when I started the numerical, a classic example that I don't want to pat my own shoulders, but I think one of the Austrian cases and what we did at MIT was the first three-dimensional numerical approach to a tunnel. So I think in Austria and MIT was the first. Now today that's basic. Everybody does a three-dimensional numerical approach. But the analytical methods, they still have their place. Number one, to have something straightforward, simple that you can do quickly. And the other one is to double-check the numerical method. That's very important.
Yeah, that makes sense.
Yeah.
Which tunnel was that in Austria?
That I don't remember. That I can look it up. And
okay. No problem.
The one I'm certainly familiar with, which we did, was they built a subway in Atlanta, and they built what eventually became a station, the Atlanta Test Tunnel, and that was because at that time subway construction had not been done frequently. There was this very big development, a subway development in Chicago, where Peck and Tatsagi was involved, and then also New York City. But then Atlanta, sort of in the 1970s, early 80s, that was the first big new subway construction. And so they built this test cavern because they didn't have a lot of experience how to build underground caverns. And we did a 3D approach to that. So that was the first one, a numerical, I would say.
Okay. Interesting. What I'd be curious is, I hear every now and then that people are afraid that especially the easy numerical modeling that we can do today, it lures people into just basically playing with the software, producing fancy, colorful images on the screen, but they don't really understand what's going on anymore, and they plug it in their software, they use it somehow, and then they take this for granted, and that's it. And what is your take on this discussion?
No, that's a fair statement. One has to be very careful. That's the reason why I mentioned that you always should check it. You cannot check the complete design with analytical methods, but at least sort of spot check what you came up with numerically. You definitely need to do that. Otherwise it won't work. As you know, there's sort of these fantastic imaging possibilities are a little bit tempting, but they're also useful, but one has to be careful.
Yeah. Yesterday at the conference, in the panel discussion, we got a interesting question, I think, where somebody asked, why not just basically get rid with the design at all, just get a very basic geological understanding, and you can base the rest of the design on observations as you go, and rely heavily on monitoring, on deformation measurements, stress measurements, and by that basically design as you go and just cut out the preliminary design.
Well, you got the answer yesterday that I think you don't want to do that because in principle, the observational method should be used in tunneling, no doubt, but not having a basic approach, and that's what many people misunderstand about the observational method. The observational method is not design as you go. The observational method is to have several designs, and you go with one, and then you see if that works, and if that doesn't work, you have a other design that will be more appropriate to what you observe. So you need to have design approaches in your pocket in the observational method. You cannot simply go ahead and that would be dangerous, particularly in tunnels where you can kill people. So
because it's basically going back to the ancient method and just starting to dig.
No, you don't want to do that anymore.
You don't want to do that. I wanted to ask you for another comment because I'm originally from Austria and now I'm working here in Norway at NGI. And in the last, 30, 40 years, there was this ongoing dispute between basically Austria and Norway that the new Austrian tunneling method versus the Q system. And there were some very prominent authors behind these disputes. And now I find myself often stuck in between these worlds, that the Norwegians, they look at me funny because they think I am the ambassador of the NATM, and the Austrians question, why do I go to Norway? And on this Q versus NATM dispute, do you want to comment on that?
I don't think this is, I think this is completely different. The NATM, it's always a bad idea to name a method by the country it comes from, because it immediately raises problems or creates problems. So the NATM, there are two basic principles. I don't have to tell you, but two basic principles. That it's an application of the observational method with quite intricate measurements, which is what you should do. And then the other thing, which I actually just mentioned before, is to mobilize the shearing resistance, or I shouldn't say shearing resistance, mobilize the resistance of the ground by letting it move. So that's the deep NATM. And then the construction process is different, because very often you cannot excavate the full size opening because of the difficult ground conditions. So you have to subdivide. That's particularly the case, which they then came up from, for instance, in Munich the first time, where they subdivided the underground opening to make it stiff enough and they still had some failures, as we all know. So that's one approach. Norwegians, one has to be careful, because there are also bad ground conditions in Norway. It's not only very good rock, but the approach to, as much as possible, to excavate the full-size opening and then put in whatever the support needed by, be that the Q method or any other method. It doesn't have to be the Q method. You basically can classify the rock and then get a support. And quite clearly what the most recent version of the Q method and has very detailed types of support, which are, some of them are general spot bolting and regular bolting, that's done worldwide. But then the ribs, that's a Norwegian development, which, by the way, is not that old. That's a relatively recent development. So that's very classic to what you should do with a rock classification / empirical method, that if the construction process evolves, then you need to adapt the method, and the Q method has done that, and the NATM has done it. So I don't see the necessity to sort of contradict one or compare one to the other and say one is better than the other. They're both entirely adequate for what they have been planned for, and they should be used. And it's getting a little bit ridiculous because of that issue with the country name in it. They do quite a bit of quasi NATM in the US. They call it the sequential excavation method. It's basically the same thing. If you close to the surface, you cannot create the entire opening at one time, and so you put a small opening there, and so on. And then also another approach to that is the one by Lunardi in Italy, which is now used all over the world, not called by Lunardi as a Lunardi method, where you have sort of basically a set of small tunnels around what eventually becomes a big tunnel. So for instance, the new railroad station in Zurich was built that way, and the new railroad station or the new highway in Boston was built that way. So there are several approaches which, depending on the condition, are entirely adequate for that particular case.
Yeah.
And they're different because the conditions are different.
Yeah, that's also always what I like to think, that in just fundamentally the comparability between these systems is very questionable, because I don't know of any case where, you cannot build a tunnel twice with different systems.
Yeah, no, it's
and therefore it's very hard to really make the comparison. Correct, which functions better, right?
Yeah.
Talking about developments and innovation in tunneling, at NGI here we have a quite nice library. And also it's going back to a lot of works from Terzaghi here. And a year ago or so, I was looking at one of the Terzaghi's, I would say, bigger influential works, the rock defects and loads on tunnel supports, that he published in 1946. And I remember when I had the first look into this, I was very surprised how modern everything looked in there. That the concepts in this book, there were some apparent changes to today, but essentially I had many déjà vus from my own studies, which were not too long ago. In another way, I also have the feeling that not much has happened since 1946 from my perspective, or from what I saw here. So what would you say, what were major developments in tunneling throughout your career or in the last 60 years?
Terzaghi, if you look at which was in 1946 when he came up with a classic classification method, that was aimed at using steel sets, or steel ribs as they call it, as a main support. Prior to that was basically into the 1940s was timber support, so that there were still some tunnels built in the 1940s. So if you look at the development, then the steel sets, and they're still used, but not as frequently. And then in World War II, the main development was shotcrete, which was developed initially for fortresses in Switzerland, and then also for the Macha power development. That's where the shotcrete was used first in tunneling. And then shotcrete became sort of a standard way of supporting tunnels. And that's also one thing that Rabchevich took over in the NATM, because it makes the flexibility of different types of supports to adapt with the observational approach that we discussed earlier. Shotcrete is ideal because you make it thick or less thick and so on. And then bolting came in. more or less simultaneously with shotcrete. That I may not be correct. I think it came from mining, but I'm not necessarily correct with that. And so today we have the definitely the combination of bolting and shotcrete, and that's what basically we talked about, is the Norwegian approach. But it's also the NATM. The only other thing that the NATM was, and I was sort of chuckling yesterday, because the Norwegians have these shotcrete ribs, and the NATM has these light steel mesh ribs. So basically similar concepts. So the light steel or the shotcrete ribs are basically replacing steel sets, because they can be put in. But steel sets are still used, depending on what the conditions are. So you see that from a construction point of view, and then in addition quite really TBMs. So that's, I would say, shotcrete bolting is sort of what evolved since World War II, or a little bit after World War II, as a major construction development. And then quite clearly, the even drilling and blasting, that came from the Swedish development. The boring speeds of traditional drilling is incredibly about 6 times as fast as it used to be. So that's that development. So that was, I don't think, clearly tunneling is a very conservative old method, but there were certainly very important new developments the last 50 years.
Yeah. When let me put it that way, I have seen very old drawings of tunnel boring machines, so I think the idea of TBMs goes back very long. But when did TBMs really become a serious tunnel construction method?
That came with Robbins. As you said, actually there was and it actually excavated a distance for the attempt of a channel tunnel in the 19th century. So that was actually a tunnel boring machine that they used, and I don't know the distance, that's a significant distance that they drilled, then they stopped it because of military reasons. So that's way back. And then Robbins, I would say, I don't know the exact number, but around 1950. And then the rest is history, because then so that was a hard rock tunnel boring machine. And then came the development, I think sort of simultaneously in Japan and Italy, these machines that the earth pressure balanced on the slurry machines. I don't know exactly when that occurred, but more or less simultaneously in Japan and in Italy. And that's basically what we have today. We have hard rock tunneling machine, we have the earth pressure balance, we have the slurry, and then we have also some that can do both.
Since we talk about developments in tunneling now, what do you think, what drives development and innovation in tunneling? Is it, perhaps one can say, is it the carrot or the stick? Is it the possibility for optimization, or is it just following regulations, following other disciplines like structural engineering? What drives innovation in tunneling?
I would say cost. Because it's still, as we discussed at the very beginning, it's still expensive. And then quite clearly, the faster you can go, the cost per length decreases. So that's basically what drives. I would say that's the main driver of the. Then the other one is creating bigger and bigger underground openings, so that rather than having 2 tunnels, have 1 big tunnel. So.
What do you think today, besides costs and of course the service demands for the tunnel? Another big topic is sustainability and resource consumption. And there, of course, I would say that a cheap tunnel today might be a very expensive tunnel in the future, and also a one that consumes resources over time a lot. How do you think that this focus on cheap tunneling fits together with the need for sustainable development?
To be honest, I don't know. Clearly, you have the components that create the cost. One component quite clearly is whatever, if it's a standard drilling rig or if it's a TBM, that consumes some materials and also some resources. If you talk about steel, so if you go all the way back, then now people are talking a lot about green steel, so that would make this a little bit more environmentally interesting. But the actual tunnel itself, again, we use concrete, which we know cement is pretty much a bad thing with regard to environmental effects. Replacing cement with something that is more environmentally friendly, that would be a way to go. But then a thing that already happens is the reuse of the excavated material to then create a support. So that I'm pretty much familiar with what they did in the Gotthard Base Tunnel, and that's a standard way today, particularly for long tunnels, where you can have a sort of facility that develops the material that comes out of the tunnel. And so that's a good way of making it more environmentally friendly. And then, interestingly, again, I have to be a little bit careful because I don't know the exact details. They're building right now a second tube for the Gotthard road tunnel. And in addition to what I just said, the reuse of material for the support, they also use the material to do some protection in some of the lakes on the north side of the Alps, sort of a bank protection by dumping the material into the lake. So that's also an environmentally advantageous use of what happens with regard to tunnels. But beyond that, I don't know where the future goes. It's a material issue, and quite clearly it's also an issue of fabricating equipment that is more environmentally friendly than the present one. But how that goes, I have no idea.
Okay, yeah, that's for sure a challenge, of course. Yeah, quite astonishingly, I think many listeners will also find this quite amazing that you yourself are also using artificial intelligence recently, or you're doing research in AI in tunneling, right?
Well, I made a nasty comment yesterday, so I'm not repeating that one. I went into this, and again, usually what I do with my PhD thesis students, I let them take charge. And so what happened is that we used artificial neural networks in the Bangkok subway system. And that was possible because that student was a Thai student, left MIT for a year and collected an incredible amount of data. So that's basically what the basis for machine learning. And essentially what he did, settlement data, advance rates of tunnel boring machines and so on. So we had an incredibly large set of data points, and then it was possible to use artificial neural networks to make prediction of settlement based on the advance and other aspects of the tunnel boring machines. These were EPBMs, and depending on how fast, what the geometry was, how deep they were, if they were tipping or not. So we could relate all these things to so basically what today everybody would call ML. And practically artificial neural networks are part of ML. So we use that, and quite successful. So we basically could make predictions and then validate these predictions based on what was observed. And then I let it drop, and then now with Professor Sousa, who did a detailed study of the Porto metro in her PhD thesis, and also created a model, not an ML model, a basic traditional model. And we're now using this to, because we have all the data, we're using this to advance the issue of not knowing ahead of the machine what's there and how this affects what then the machine encounters. And so that's basically what we're working on right now. And there's a PhD thesis under her supervision in Stevens that is an initial step. So I'm a little bit careful with these things because, but on the other hand, they are useful.
Okay, yeah, that's very fascinating that you use this. I heard the analogy several times now that people who let's say witnessed the upcoming of numerical modeling in our field, they also say that in the beginning there were a lot of rather silly applications, and over time it took time to mature. Do you also see something like that or foresee something like this for artificial intelligence?
Well, sure. If you apply the methods and then some, you say, okay, well, why did we use this for? There could be a much simpler way of doing it. Or that's really where there's a lot of advantage of using a new approach, independent of its AI or whatever. That's classic. Yeah, I agree.
And what do you think? What will be the implications of technologies like artificial intelligence for tunneling in the future?
Well, I cannot generalize. I can only tell you what Rita and I are doing. We have, I don't know how many sensors are on a tunnel boring machine, an incredible amount. And they read information at second intervals. So we have data, an incredible amount of data. How can we use that to improve the performance of a TBM going through the ground? That's the fundamental question. And it comes down to the main question is, because we do not know what's ahead, how can we use all this information to make a prediction for how the TBM should go the next meter? And that's still a question. Lots of people working on that. I think thousands of people working on that in that sense. It's a logical question. Where we're going to get, I have no idea.
It's always hard to make predictions in tunneling and into the future.
So, but it's a logical approach. So that's the reason why so many people are doing that. And
for sure. I mean, talking about research topics now, where do you see the largest research gaps in tunneling, or where do we have the biggest need to further advance tunneling?
A good question. It's what we just discussed. So how do you improve your knowledge of what's going on and use that knowledge in, again, what we talked way back, the observation approach. So the tunnel boring machine or drilling and blasting, you go ahead and then you want to, as closely as possible to the ground structure interaction that you want to use that information to have an optimum ground structure interaction for the final tunnel. So there's still some work to be done how to use this. So be that you can use a core boring ahead of your tunnel boring machine, and then you have a core. What do you do with this core in order to make a better prediction for having an optimal ground structure interaction in your final? So that's still a fundamental question where there are sort of lots of subtopics that could be used. And then I don't know. There may be new materials coming in, and then quickly you need to consider what these new materials do in contrast to the existing ones.
What do you think about tunnels in increasingly challenging ground conditions, like very soft rocks, very heterogeneous conditions at the interface between soil and rock and these kinds of things?
I think that always existed. So I don't, I have no idea if there's anything beyond the traditional ways of dealing with this, freezing, grouting. There may be, I have no idea, but there may be different grouts, although sort of chemical grouts other than cement-based that might be better suited for a particular condition. But the basic underlying principle that you have something that cannot hold up by itself by reinforcing it internally, which we grout, or externally by the support that we were talking about, bolts and shotcrete. I think the basic principle is still going to be the same. And people have been using this for quite a while.
I would like to wrap up with a final question. Do you have advice for future generations of tunnel builders and engineers?
Get involved. No, it's a fascinating area. I think I'm glad I got into it. But and how particularly all young people will feel the same way, that building a tunnel is a fascinating thing to do. So it depends on the person. If they think it's equally fascinating, go ahead. If they don't, let it drop.
Absolutely. Yeah. Herbert, thank you very much for being on the NGI Technical Podcast. It was great to have you as a guest.
Thanks for inviting me. I hope this works out.
Absolutely. I'm very positive they make the best out of this. Yeah. Thanks.